Hi, I'm your instructor, Nancy Boyens. Welcome to the lecture today. Our topic for today is measuring and selecting color. Now, why do you think you might need to measure color? Well, let's imagine you're working at a print shop and you're working the front desk one day, and a gentleman comes in, and he's a salesman from out of town, and he brings you his brochure, and he says, I've run out of copies of my brochure, but my boss has given me permission to have some reprinted. Can you do that for me? And I don't know what exact color number this is, but I do know that people at my office are really picky that the front of this brochure is this green, and it's our real signature shade of green, and I want you to do everything you can to copy that color exactly. If he was able to give you something like a colored number in a numbering system, that would make that job a whole lot easier on you. So that's one reason we might measure color. Also in this lecture, we're going to look at some issues like what color combinations are supposed to go well together. And there have been articles written about that topic for hundreds of years. So we'll look at some of the things that have been said about that in the past. Okay. Now, to get going here, we're going to talk about two major systems for describing color. We're going to look at something called the color wheel for light. And computer monitors and everything dealing with color in the computer world is based on that system. We're also going to look at another color wheel called the color wheel for paint. And it's what's used in the printing industry. And it's also what's used as the basis of a lot of these articles when they talk about what colors go well together. They'll talk about, what happens when two colors are opposite each other on this wheel or next to each other on this wheel. So when they are referring to that, they're going back to the color wheel for print. All right, so let me start talking a little bit about the color wheel for light. And in this system, there are three primary colors. They're called the additive primary colors, and they are red, blue, and green. Those are what are the broad areas on the rainbow. Then we have colors that are placed in between those on this wheel that looks like a Star of David that you should be looking at, that are called the subtractive primaries or the secondaries. And those are cyan, which is really a turquoisey kind of blue. Usually a very bright blue. I don't know that I have it recreated as bright as it should be on this slide. And magenta and yellow. Now, I mentioned that the three additive primary colors, red, green, and blue, are the broad areas of the rainbow. If you were looking at a rainbow, you'll see that the reds are down at one end. And actually, if we were measuring light, there are some color frequencies that go beyond what the eye can perceive and pick up. So what's beyond red would be the infrared shades or frequencies. Then at the other end of the spectrum are the blues. And again, going into the frequencies of light that we can't see, you would be getting into the ultraviolet frequencies. And then in the middle of the rainbow are the green colors. Okay, so something kind of interesting happens if you isolate these separate parts of the rainbow and you had something that was a pure frequency of red and you placed it on top of something that was a pure frequency of green. And things happen when you combine light frequencies that don't happen at all when you would combine something like paint. If you place red, blue, and green light beams crossing each other all on top of each other, the result that you get when it would shine on something like the wall would be white. So red, green, and blue combined together make white light. And of course that's not at all what you see when you combine paint. Now also on this wheel you see what I have listed as the subtractive primaries, which are cyan, magenta, and yellow. To actually create those, if you combined the red light with the blue light, you do get the color that goes in between, which is magenta. Now that one seems logical to us. We can kind of see how red and blue might make magenta. It doesn't make sense to us, again with all of our experience of blending paint, to think if I crossed a blue and a green beam of light, I would get cyan. What really doesn't seem to make sense at all is that if you cross a red beam of light with a green one, you get yellow. It just doesn't seem to go that red and green make yellow, but in light they do. Now, why do I call these the subtractive primaries? Well, it's interesting, something else that happens. If you use one of the colors that's opposite another one on this wheel, they can have the effect of the ability to cancel each other out. For instance, one thing you may not notice with your naked eye, but certain types of light bulbs give off some color. Like the long tubular fluorescent light bulbs actually give out some green. Now, if you sit under that green light for a while, you will cease to notice it because your eye is smart enough to kind of filter that out. But if you were to go in there, say with traditional film camera, and open up the aperture of the lens enough to where you did not need to use a flash, and just take the picture in there, what you might see is that your picture would turn out with a lot of green on it. So what photographers have done for years is they'll put a little filter over their lens that's magenta, and the magenta has the ability to cancel out the green. So these all do that for the color that is opposite them on the wheel. They have that ability to neutralize the other color and cancel it out. Okay, so now let me have us look at a color wheel that we're more used to seeing. This is the color wheel for paint. The primary colors in this system are red, blue, and yellow. Now, we've probably all seen that. If you bought a watercolor kit, you might have had one with 30 shades, but you might have had one, they do sell a few that just have red, blue, yellow, and black ink. And so you would combine paint to get the shade you wanted. So you would combine your red and blue and get purple. And that's the way things work on this color wheel for paint that we're looking at. So red and blue combine and get violet. And so there we get the secondary color that we place in between. Yellow and blue combine to make green, and yellow and red combine to make orange. And so you combine any of the two original primaries, and you get the secondary that we place in between it on this wheel. Okay, so when we look at the issue of what colors look good together and start reading a lot of articles that have been written about that, what they're actually using is a broader thing called the 12-hue color wheel. And they're using the color names of 12 colors. Now, we've had 6 that we've been looking at on our color wheel for paint. But to get the 12-hue color wheel, what you do is you combine 2 colors that are next to each other on the wheel, like red and orange, and then you place the resulting shade in between, and they have totally logical names like red-orange. So this third set of colors are called the tertiary colors. So if the second set were the secondaries, tertiary really just means 3, and so this is the third set. So the colors we get in the third set are red-orange, red-violet, blue-violet, blue-green, yellow-green, and yellow-orange. You know, you'll go out possibly on the web and search for articles about what colors, again, let's say, go good together. And you'll be reading along, and they'll be talking about 2 colors that are distanced a certain way on the wheel, like they're opposite each other, or they're next to each other, or they're triangularly spaced evenly from each other. And sometimes you'll be reading this article and you'll have assembled your own 12-hue color wheel like I have on the slide, and you'll be looking at the color that's here, and the one that they mention is opposite, and they're using some different color names than what you see across from each other. Well, you know, really, they say they're basing all this on the 12-hue color wheel, and that's what they've said all the way through their article. But in reality, they're actually going back to a version of a color wheel that was created by Isaac Newton. And Newton had his color wheel, and instead of a wheel with, we've got separate little spots of color on it, his was a continuous wheel. And what he did was he gave different amount of space to different shades based on how often he thought they occurred in nature. So he thought the thing that occurred the most were the blues. So he gave more space to the blues. So when we're talking about what's opposite each other on the wheel, instead of just these 12 exact colors being evenly spaced, they really are looking at this wheel created by Newton, and they're using Newton's spacing to be across from a shade. So So you will find if you read some of these articles, something may not seem to make sense to you, and that's really what's going on.